Okay, everyone, good afternoon. Welcome to Module 2, and well, this is Lisa. So we're going to kick things off today with the quiz review from Tuesday before we continue on with the rest of Module 2 of the Stormwater Management Design Review course. So, all right, let's look at the quiz. All right, so the first three questions of the quiz were just identifying information. So the quiz actually starts with question number 4. This is the actual first question. Okay, so the 6 minimum measures are required by what type of mandate? All right, well, the answer is A. The National Pollutant Discharge Elimination System, or NIPES, Phase 2 stormwater regulations require that the 6 minimum measures be implemented for small MS4s. Question 5 is reviewing site plans is required to comply with which statewide basic requirement? The answer is C. The post-construction statewide basic requirement requires that the permittee develop, update, implement, and enforce its stormwater management program to address runoff in new development and redevelopment, including reviewing projects to ensure they comply with the stormwater management rules. Question 6. Who's responsible for enforcing the post-construction stormwater management program? EPA, NJDEP, the Soil Conservation District from the county, or the MS4 permittee? Well, the answer is D. The MS4 permittee is required to develop, update, implement, and enforce its stormwater management program to address runoff in new development and redevelopment. Question 7. Under the SCO pursuant to the 2026 rule amendments, what is the definition of major development? Is it the disturbance of 1 or more acres of land since February 2nd, 2004? The creation of 1/4 acre or more of regulated impervious surface since February 2nd, 2004? Or the creation of 1/4 acre or more of regulated motor vehicle surface since March 2nd, 2021? Or is it the reconstruction of 1/4 acre or more of motor vehicle surface or impervious surface since January 20th, 2026? Well, the answer is E, all of the above. Pursuant to the MS4 permit and NJAC 7:8, the SCO shall define major development as defined in subsection 1.2 of the Stormwater Management Rules. Question 8. Which of these can be used to demonstrate compliance with the water quantity design and performance standard? Okay, there's 3 here, and the answer is B. Design stormwater management measures so that the post-construction peak runoff rates for the current and projected 2, 10, and 100-year storm events are 50, 75, and 80% respectively of the pre-construction peak runoff rates. Question 9. Which of the following is the New Jersey water quality design storm? Is it 1.25 inches in 2 hours, or 1.25 inches in 24 hours? Or is it the 1-year storm? Or is it 1 inch of rainfall? The answer is A. The New Jersey water quality design storm is a storm with a variable intensity that results in 1.25 inches of rainfall in 2 hours. Question 9. Which of the following is the new, sorry, why didn't it advance? Question 10. For a project with 2 acres of asphalt parking, where the base of the motor vehicle surface will be completely removed and replaced with new roadbed materials and paved, is the project subject to the water quality design standard? The answer is yes. Pursuant to NJSC 7:8-1.2, the replacement with new roadbed material is a disturbance and is also a reconstruction of motor vehicle surface. Therefore, the project is subject to the water quality standard at NJAC 7:8-5.5A. Question 11, which of the following would meet the groundwater recharge standard? The answer is D. Infiltrating the increase in the projected 2-year storm volume or maintaining the average annual groundwater recharge are the two options for meeting the groundwater recharge standard. Sites in an urban redevelopment area are exempt from the groundwater recharge, but please take note of the asterisk. The definition of urban redevelopment area specifies only previously developed portions of a site are exempt. Therefore, demonstration of any of these three things, if done properly, is acceptable. Question 12. True or false? A project located in a tidal flood hazard area is always exempt from the water quantity standard. Well, the answer is B, false. In a tidal flood hazard areas, the water quantity standard does not apply only if the applicant can demonstrate that the increased volume of stormwater runoff will not increase flood damage below the point of discharge. In tidal flood hazard areas, stormwater runoff quantity analysis is required unless the design engineer demonstrates through hydrologic and hydraulic analysis that the increased volume, change in timing, or increased rate of the stormwater runoff, or any combination of the three, will not result in additional flood damage below the point of discharge of the major development. No analysis is required if the stormwater is discharged directly into any ocean, bay, inlet, or the reach of any watercourse between its confluence with an ocean, bay, or inlet and downstream of the first water control structure. Question 13, true or false? BMPs from table 5-2 can be used to meet stormwater quality requirements without obtaining a waiver or variance from NJAC 7:8-5.3. The answer is false. BMPs from table 5-2 can be used for stormwater runoff quantity only. For them to be used for stormwater runoff quality, a waiver or variance from subsection 5.3 in the rules must be obtained. Question 14, true or false? A gravel area used for vehicle parking during events that are regularly held should be considered a motor vehicle surface. Well, the answer is A, true. A surface that is intended to be used by motor vehicles beyond an emergency situation should be considered as part of the total motor vehicle surface. Now, in the case of an access road that is gated or accessible to motor vehicles only in an emergency, for example, the overall use of the surface, except in an emergency, does not allow for motor vehicles to use the surface, and the reviewing agency may determine that the area can be excluded from the total motor vehicle surface of the site. Question 15. Which of the following is required in a maintenance plan? Cost estimates, specific preventative and corrective maintenance tasks, the name, address, and phone number of the responsible party, or D, all of the above? The answer is D, all of the above. All of these things must be included in the maintenance plan. Question 16. Which of the following cannot be the responsible party for maintenance of a stormwater BMP? Is it A, a municipality, B, a homeowners association, C, a tenant of an individual property in a non-residential development, or is it D, a homeowner that owns only one home in a large residential development? The answer is D. The stormwater management rules at NJAC 7:8-5.8C state that the responsibility for maintenance shall not be assigned nor transferred to the owner or tenant of an individual property in a residential development or project unless such owner or tenant owns or leases the entire residential development or project. Question 17. At a minimum, how often is the responsible party required to evaluate the effectiveness of the maintenance plan? Is it 5 years, 2 years, 1 year, or only if there's a change in the B&P design? The answer is C. The stormwater management rules state that the responsible party must evaluate the effectiveness of the maintenance plan at least once per year and adjust the plan as needed. 17. I'm sorry. What? Yeah. 18. True or false? All maintenance plans for stormwater management measures must be recorded on the deed of record for each property on which the maintenance must be undertaken if the responsible party is not a public agency. The answer is true. Per subsection 5.8 of the stormwater management rules under item D, if the person responsible for maintenance is not a public agency, the maintenance plan and any future revisions shall be recorded upon the deed of record for each property on which the maintenance must be undertaken. Question 19, true or false? When choosing a hydrodynamic separator type MTB, the inlet configuration, such as the angle and number of inflow pipes, must strictly match the inlet configuration described in the NJCAT verification report. The answer is true. When the NJDEP certifies an MTD, such as a hydrodynamic separator type, only the configuration as tested by NJCAT is certified to provide the indicated TSS removal rate. Manufacturers will frequently offer other configurations claiming certification, and these will include an inlet or outlet configuration that is not 180 degrees apart and may have multiple inlet pipes. Okay, maybe a great inlet. So deviations from the tested and certified configuration are not certified and cannot be used to achieve the TSS removal rate found in the certification letter. Okay, so that was it left over from Module 1, and Peter is up next to begin Module 2. Peter, let me know when you're ready to begin.
All right, thanks, Lisa. I'm ready to go. I'm going to be sharing my screen now. Just one more moment here. All right, so good afternoon, everyone. Once again, my name's Peter, and let's get started on, let's really get into Module 2 now of the Stormwater Management Design Review course after Lisa went through that quiz review that was kind of carried over from Module 1. So here's the agenda for today for the remainder of Module 2. So we'll begin the day with a presentation on stormwater calculations presented by myself. Then we'll move on to soil testing presented by Lisa Schaefer. And lastly, green infrastructure, focusing on the GI fact sheet, also presented by Lisa Schaefer. And then after those three presentations, we'll have quiz number 2. And the end of the day will be the quiz review, which will be presented by me. We'll also take a quick break somewhere in between all that. All right, so let's get started with our first presentation for today, excluding the Quiz 1 review, which is going to be on stormwater calculations. So this material is included in this course because DEP has found from previously conducted audits of MS4 permittees that stormwater calculations are oftentimes not performed correctly. So while most of you are probably familiar with these methods, as evidenced by some incorrect calculations and some of the projects submitted for audits, we're including this brief review in the course. Presentation goals. The first goal of this presentation is to understand the Natural Resources Conservation Service, or NRCS, methodology, formerly referred to as TR55, and how it is used to calculate the peak flow rate and volume of runoff to produce hydrographs. The next goal is to actually use the NRCS methodology to calculate the volume of runoff. The third goal is to calculate the time of concentration, and we'll cover some of the examples from Chapter 5 of the BMP manual. Next, we'll take a more detailed look at hydrographs and rainfall distributions. Then we'll cover how to use the NJDEP two-step method for calculating runoff from an unconnected impervious area. And lastly, we'll discuss when exfiltration may or may not be used in stormwater calculations. So first, we'll take a closer look at the NRCS methodology. Per NJAC 7:8 5.7, the design engineer shall calculate runoff using the NRCS methodology, as described in the National Engineering Handbook, or NEH, and as additionally described in Technical Release 55, or TR55. However, please note that the TR55 manual has been superseded by Part 630 of the National Engineering Handbook. And if you are using the TR55 manual, you'll be using outdated equations and values. A link to the NEH is provided at the bottom of this slide for that reason. As mentioned before, the NRCS method is used to calculate the peak flow rate and volume of runoff and to produce hydrographs, which are flow of water over time. The NRCS method uses unit hydrographs, rainfall depths, rainfall distributions, curve numbers, and times of concentration, which are all dependent on geographical and topographical differences that affect how rain will fall over a specific area. And we'll review all of that on the upcoming slides. Now, there are numerous software packages that use this technology, and in later presentations, you'll learn what to check for in your reviews. It's important to note that the NRCS method can be used for a drainage area of any size, but per 7:8, the design engineer shall consider the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces separately to accurately compute the rates and volume of stormwater runoff from the site. And I know that's a lot of words, so we'll go over exactly what that all means and looks like in a couple of slides. The NRCS methodology uses the curve number, or CN, runoff equation to calculate the runoff depth, Q, in inches, where P is the rainfall depth of whatever storm we are looking at. S is the maximum potential retention, which is the maximum infiltration capacity of the land surface and soil. And that value is based on the curve number, which we will go over on the next slide. And then IA is the initial abstraction, which assumes 20% of S is intercepted or infiltrated before runoff actually occurs. This equation then simplifies to the one on the bottom right of the slide. So what does this equation tell us? It tells us that not all of the rain that hits the ground actually turns into runoff. The curve number, once again abbreviated CN, is an empirical parameter used for predicting infiltration and direct runoff from rainfall. CN is a function of the hydrologic soil group, or HSG, and the land cover, such as woods, open space, agricultural use, impervious cover, etc. HSGA is the most permeable soil group and produces the least amount of runoff when thoroughly saturated. The designations then go alphabetically from B to D, with D being the least permeable soil group and having the highest runoff potential. The preliminary HSG classification can be found on the NRCS Web Soil Survey website, but further investigation may be necessary. And Lisa will dive deeper into all of this in the next presentation. Once you have determined your HSG, or are using the defaults that are allowed, you can determine the CN value to input. Shown on the right side of the screen is Table 9-5 from the National Engineering Handbook, which details runoff curve numbers for urban areas. There are other tables for agricultural lands, arid and semi-arid rangelands, Puerto Rico, and Hawaii, but these are the curve numbers that you will see the most. Generally speaking, the larger the CN, the more runoff volume. That is why the CN increases as the HSG goes from A to D, and why the CN increases as imperviousness increases. And it is important to note that for an impervious surface, regardless of the HSG, the curve number is 98, meaning that the S value we talked about before is close to 0. Practically no rain will be retained by the land surface and soil. It is also crucial to use the CN value that best aligns with the land cover in HSG. So please note the requirement from the stormwater management rules shown in the yellow box on the top left side of the screen. This requirement means that a lower CN, associated with good conditions and good cover, shall be presumed in the pre-development conditions in order to be conservative. The arrow on the right indicates the row where this CN value is for open space. Also, please note the information in the white box on the bottom left side of the screen. This note means that the values in the red box on the table are not what you will typically see in your calculations for a project, because they are for large-scale watershed modeling and not typical land development projects. And please note that the row for developing urban areas is not used for stormwater management calculations, but it is used for soil erosion calculations. So what do you do when you have more than one curve number on a site, which most, if not all, sites will have? Because the CN runoff equation is nonlinear, meaning the output does not change proportionally to the input, you cannot use an average CN value to compute the volume of runoff for an entire site. Doing so greatly underestimates the volume of runoff generated by impervious surfaces. Unfortunately, this is a common error we find in our audit reviews. So let's look at an example to really understand this concept. Say we have a site with 1 acre of impervious and 2 acres of lawn. The impervious area has a CN of 98, and the lawn area has a CN of 65. If we average those values and compute the volume of runoff, we get 1,089 cubic feet. Now, if we calculate the volume of runoff separately for impervious surfaces and pervious surfaces, and then add them, we get 3,811 cubic feet. That's a massive difference of 71%. So ultimately, what happens when an average CN is used? Number one, the BMP is undersized. And number two, the BMP does not merit the pre-approved TSS removal rate. So this greatly affects the function of the BMP. Here's another example directly from Chapter 5 of the BMP manual. Please take a moment to read the slide. As a note, this example mentions the 2-year design storm and does not make a distinction between the current or projected 2-year storm event. That's because that's not the purpose of this example. The purpose of this example is to enforce the idea of separate CN values. So from the example diagram, we see that the runoff from the impervious surface will flow directly into the grass swale, as will runoff from the pervious surface. So how do we calculate how much runoff is actually getting to this swale? Starting with the CN values for each segment from Table 9-5 in the National Engineering Handbook, the CN value for the pervious area, which is lawn area with HSG of A, is 39. And as mentioned before, the CN for the impervious area is always 98. Next, using the CN runoff equation, we'll calculate S, which again is the maximum potential retention, also known as the maximum infiltration capacity of the land surface and soil. This is where the major difference is. You have 15.64 for the lawn area and 0.204 for the impervious area. Empirical data tells us that 20% of this value will then be intercepted or infiltrated before runoff actually occurs. That comes out to 3.128 inches for the lawn area and 0.041 inches for the impervious area. That's why for small rain events like the water quality design storm, which is only 1.25 inches, it's imperceivable on lawn area because there's no runoff. But on an impervious area, that small storm can still create a lot of runoff. So calculating the numbers separately, we get 10.8 cubic feet for the lawn area and 1,362.5 cubic feet for the impervious area, for a total of 1,373.3 cubic feet. But using an average, as shown on the right side of the screen, we get 508 cubic feet, which is 63% less. All right, so that's not okay. Moving on to goal number 3, we're going to talk about time of concentration. Time of concentration is defined as the time required for stormwater runoff to travel from the hydraulically most distant point on a site to a point of analysis. Let's take a look at the next slide to really understand what this means. So when talking about time of concentration and point of analysis, we are talking about a drainage area. And a drainage area is a portion of land where all the stormwater runoff produced by that area converges to a single point, a point of analysis. For example, in this graphic, any drop of water that falls in the valley between the two yellow shaded areas, which are ridge lines, will eventually make its way to the river, and then to the downstream point of that river. And any drop of water that falls on the other side of the ridgeline will go somewhere else. So a drainage area is everything that will eventually make its way to the same point of analysis. And it's extremely important to remember when reviewing plans that a drainage area does not stop at the property line. You have to look at the offsite area surrounding the property. And a project can have one drainage area or multiple. There can be small drainage areas and big drainage areas. It really depends on the topography and potentially the stormwater management infrastructure. Because perhaps, even though topographically the water is going one way, if it enters a stormwater management system, it could be directed somewhere else. Now back to the time of concentration. The time of concentration is the hydraulically most distant point. That does not mean the farthest point. It depends on surface roughness, slope, and channel shape if there's channel flow. For example, a drop of water on pavement will travel faster than a drop of water in a forest. A smooth surface versus one with obstructions. And a drop of water on a 10% slope will travel faster than a drop of water on a 1% slope. Additionally, the energy level of the runoff also factors into the calculation. There are three energy levels or flow that may occur: sheet flow, shallow concentrated flow, and channel flow, with sheet flow and shallow concentrated flow being the most common. Looking at these more closely, sheet flow is usually at the headwaters and over plane surfaces. This is where runoff forms a sheet that is low in energy and also low in velocity and depth. So the depth would be less than 0.1 feet. Shallow concentrated flow occurs where runoff begins to merge and concentrate, hence the name. The velocity and depth increase, so there's a slightly higher energy, but there is still no well-defined channel. And lastly, channel flow can be seen in aerial photographs and on GIS and USGS maps, blue lines for streams or dashed lines for pipes. It is a well-defined channel, open or closed, so a stream or a pipe, that has deeper and faster flow, so that would be the highest energy level. Now that we've covered the properties that affect the time of concentration and the types of flow you can expect to see, let's take a look at the actual equations. From the National Engineering Handbook, the velocity method can be used to calculate the time of concentration. This method assumes that the time of concentration is the sum of the travel times for each segment of flow along the hydraulically most distant flow path. And we'll talk about what a segment is over the next few slides. In the meantime, please note that there is no longer a minimum time of concentration. Per Chapter 5 of the BMP manual, there used to be an assumed minimum of 6 minutes, but now you have to accurately calculate the time of concentration for each drainage area. Additionally, the maximum sheet flow length, as per the National Engineering Handbook, is 100 feet for pre-construction conditions. However, the sheet flow can be less if there is a physical constraint that prevents sheet flow from occurring, such as coming into contact with a curb, swale, or inlet. But the maximum is 100 feet. Now for the post-construction conditions, the maximum sheet flow length should not exceed either the McEwen-Speece limitation or 100 feet, whichever is less. And the equation to calculate the McEwen-Speece limitation is noted under the second bullet, where L is the sheet flow length, S is the slope, and N is the Manning's roughness coefficient. So if the sheet flow length calculated by the McEwen-Speece limitation criteria is less than 100 feet, you have to use that length. But if the sheet flow length determined by the McEwen-Speece limitation is more than 100 feet, the sheet flow length must be limited to 100 feet. And remember, the sheet flow length can be less than both of these values if there is a physical constraint present that prevents sheet flow from occurring, just like in the pre-construction conditions. Now that we've covered sheet flow limitations, let's take a look at the equation. And remember, each flow type, sheet, shallow concentrated, and channel, has its own equation, and this one is for sheet flow. So it uses a simplified version of Manning's kinematic solution, and listed here are the parameters for that solution. You need the sheet flow length, which we just talked about, Manning's roughness coefficient, the current or projected 2-year 24-hour rainfall, depending on if you're looking at current or future values, and the slope of the land surface. Diving into Manning's roughness coefficient, values for sheet flow can be found in Table 15-1 of the National Engineering Handbook. For sheet flow, the roughness coefficient includes the effects of surface roughness, the effects of raindrop impact, the effects of obstacles, and the effects of erosion and transport of sediment. And the values range from 0.011 for smooth surfaces to 0.8 for dense underbrush. However, per Chapter 5 of the BMP manual, the maximum value that can be used for woods in New Jersey is 0.4, which corresponds to light underbrush. So you should never see an N value greater than 0.4 being used for sheet flow. If you do, it's wrong. Diving into the 2-year 24-hour rainfall, typical values in New Jersey range from 3.2 to 3.5. The overview presentation for Module 1 described how to get the rainfall depth for a location using either the county data or the NOAA data. So I won't go over that again. However, as mentioned earlier, this value needs to be multiplied by the current and projected adjustment factors. That means you should not see the same time of concentration for current and projected storm events. They should be different because they should be using different rainfall amounts. So in this example, the 2-year 24-hour rainfall for a project in Mercer County is 3.33 inches. And after applying the adjustment factors, that value becomes 3.36 inches for the current storm event and 3.86 inches for the projected storm events. Now, what happens when you have a site in multiple counties? Well, the precipitation values shall be prorated based on the percentage of drainage area in each county. For example, if you have a site with 1/3 of the area in Middlesex County and 2/3 of the area in Mercer County, you'll do the same calculation as before with the rainfall depth and adjustment factor, but now you'll also multiply by the percentage of area. So for Middlesex County, that would be 0.333, And then for Mercer County, that would be 2/3, 0.667. You will then add those two values for the total rainfall. All right, so that was everything for sheet flow. Let's take a look at the equations for shallow concentrated flow. Travel time for shallow concentrated flow is determined using a very simple distance over speed relationship. More specifically, the travel time is equal to the flow length divided by the average velocity times a conversion factor of 3600 to convert seconds to hours. And per the National Engineering Handbook, it is assumed that shallow concentrated flow can be represented by one of 7 flow types, and that's how the velocity will be determined. Diving into this velocity value, the National Engineering Handbook provides figure 15-4 as shown on the slide. And it also provides table 15-3, which converts these plotted curves to equations. So as mentioned, there are 7 flow types, each one represented by a curve on this graph. The x-axis is the velocity, and the y-axis is the slope. So if you know the land cover and you know the slope, you can use these curves and equations to find the velocity. I would also like to note that if you are still using the TR55 manual, they have different velocity equations. They only have 2, one for paved and one for unpaved. So again, the TR55 manual has been superseded by the National Engineering Handbook, and you need to use and see these equations when reviewing. And last but definitely not least, we have channel flow. In this case, Manning's equation can be used to estimate the travel time, and listed here are the parameters for that equation. You need Manning's roughness coefficient, which can be obtained from standard hydraulics textbooks, the length of the channel, the hydraulic radius of the channel, and the channel slope. More specifically, the hydraulic radius is the cross-sectional flow area of the channel divided by the wetted perimeter. And the wetted perimeter is the length of the cross-section actually in contact with the water. This hydraulic radius parameter aims to take into account the effects of friction along the channel because that friction slows the water down. Please note that this equation can be used for open channels, like streams and rivers, and for partially full gravity pipes, so your typical stormwater pipes. However, if you see a pressurized pipe, that is a completely different equation. Thankfully, you shouldn't see that too often. All right, so now we know how to calculate the time of concentration. So let's take a look at an example. And this example is example 5-1 from chapter 5 of the BMP manual. For a site located in Mercer County, stormwater runoff flows through a wooded drainage area along a flow path, measuring 1,000 feet in length, consisting of sheet flow over an area with 0.5% slope and shallow concentrated flow over an area with 1% slope. Calculate the time of concentration using current rainfall data. So we were given a lot of information in this prompt. We have that it's located in Mercer County. The area is wooded. The entire flow path is 1,000 feet. The sheet flow has a 0.5% slope. And the shallow concentrated flow has a 1% slope. So let's see what we can do with this information. Assuming this is for post-construction conditions, what is the first thing we need to do? So the first thing we need to do for sheet flow is calculate the sheet flow length. And we do that using the McEwen-Spees limitation because it's in the post-construction conditions. So we have 100 times the square root of the slope divided by Manning's roughness coefficient. The slope is 5%, or excuse me, 0.5%, so it's 0.005 feet per feet. And because the site is wooded, the maximum N value we can use is 0.4. Using these values, we get 17.68 feet, which is less than 100 feet, so we have to use this value. The next thing we'll do is calculate the correct rainfall depth. And we actually calculated this before for Mercer County. So the rainfall depth times the current adjustment factor is 3.36 inches. Lastly, we'll combine all of our variables into the simplified version of Manning's kinematic solution, and we get 9.12 minutes. Now, because the entire flow path is 1,000 feet, but the sheet flow was only 17.68 feet, we have to calculate the travel time for shallow concentrated flow over the remaining 982.32 feet. Using figure 15-4 from the National Engineering Handbook, we know that the land cover is woods, and we know that the slope is 1%, or 0.01 feet per feet. So if we go up to 0.01 on the y-axis and go right over to where our land cover intersects with this slope, we can then go down to the x-axis to get our velocity, which is 0.25 in this case. Plugging all of that into our equation, we get a travel time of 65.49 minutes. And finally, the time of concentration is the sum of travel times for each segment of flow along the hydraulically most distant flow path, which is 74.61 minutes in this case. So hopefully that example made sense to everyone, but if not, please drop your questions in the chat. Moving on to goal number 4, we're going to talk about hydrographs and rainfall distributions. As mentioned before, a hydrograph is a graph that depicts flow over time. And a hydrograph can provide us with a lot of information, like the time of concentration, the time of peak flow, the peak flow rate, and the volume of runoff. So it's really important to understand what they are and how they are developed. The first thing we need to do is discuss the different types of hydrographs. In a perfect world, we would use what's called a natural hydrograph, which is obtained directly from the flow records of a gauged stream. However, because this is based on past data and may be limited or unavailable, we use dimensionless unit hydrographs, or DUHs, to create synthetic hydrographs to predict what a storm will look like. A dimensionless unit hydrograph, or DUH, is basically a template or shape of how a watershed responds to rain. It doesn't have actual numbers yet, it just shows the pattern of rising and falling of runoff, and they are based on generalized empirical data. The most common one is the SCS, or Soil Conservation Service, DUH. But there are other regional ones as well, such as the Delmarva, which stands for Delaware, Maryland, and Virginia, which takes into account some regional characteristics. These DUHs are then scaled based on watershed area, rainfall depth, and duration to produce a synthetic hydrograph. Taking a closer look at what this graphically looks like, the SES unit hydrograph is the orange curve. The corresponding rainfall event is the blue shaded box. And the timing of the hydrograph is based on the time of concentration, which is highlighted in yellow. It's important to note that even after rain falls, it takes time for water to travel through the watershed and produce the peak flow at the outlet. And this delay is called the lag time. And the area under the hydrograph is the total volume of runoff produced by the site in response to the rain. This DUH has a peak rate factor, or shape factor, of 484, which means that 48.4% of the total runoff volume is discharged before the peak time, which is shaded in purple, and 51.6% of the total runoff volume is discharged after the peak time. And the time of peak flow and the peak flow rate occur at the maximum height of the hydrograph. Now, when reviewing stormwater reports, you should be able to find the shape factor somewhere, usually on the printouts from the hydrology software. So this is an important thing to check. As mentioned before, the second most common DUH in New Jersey is the Delmarva. Now, the Delmarva is suited for flat coastal areas, and shown here is a comparison of the SCS and the Delmarva. So what can you tell me based on this graph? The peak flow rate is a lot lower, but the time is a lot longer. This is because the Delmarva has a shape factor of 284 or 285, depending on the software, meaning that 28.45% of the total runoff volume is discharged before the peak time. It is also important to note that the total volume of runoff is the same between the two hydrographs. So when do you use one over the other? As mentioned before, the Delmarva dimensionless unit hydrograph is particularly suited for flat coastal areas with slopes less than 5%. Typically, the coastal plain physiographic province of New Jersey, aka South Jersey. Now, it's important to note that the same DUH must be used in pre- and post-construction development for both the current and projected storms. Now, projects that lie on or near the boundary between the Piedmont and coastal plain regions, near Trenton, Princeton, Monmouth Junction, or Carteret, should be modeled with both the SCS and the Delmarva, and the results should be compared with actual field conditions to determine which dimensionless unit hydrograph is the best fit. The municipal stormwater management plan, where the site is located, may also include this information. Another helpful tool is this interactive GIS application where you can type in your site address and find out which physiographic province you are in. And there's a link to that on the bottom of this slide. So when not to use the Delmarva dimensionless unit hydrograph? The Delmarva dimensionless unit hydrograph cannot be used outside of the coastal plain. It cannot be used in the sizing of an MTD because it will underestimate flow rates. It also cannot be used when coastal plain characteristics do not actually exist. So yes, maybe the site is physically within the coastal plain region, but if it is a completely paved site or has slopes greater than 10%, the SES should be used to better model this. So in addition to the rainfall depth, or the amount of rain, we need to know how rain falls during a storm, and this is called rainfall distribution. To achieve the goal of estimating a rainfall event for design and planning purposes, between 1961 and 1977, NRCS developed synthetic rainfall distributions from historical records for the different regions of the country. The basic shape of the distributions all assume rain starts gently, increases in intensity, and then tapers off, which gives it a bell shape. So specifically in New Jersey, we previously used the Type 3 distribution. Now there are the NOAA-C and NOAA-D distributions, and you can expect to see higher peak flow rates with these distributions. These distributions used to be solely based on county, but now the distributions don't exactly follow county lines. So this is something you will have to check when you are reviewing. And the map shown here is available in Chapter 5 of the BMP manual. The yellow shaded area is NOAA-C, and the red shaded area is NOAA-C, and the yellow shaded area is NOAA-D. And if you have any questions or concerns about what region your project falls in, please reach out to us. All right. So now we are going to do an in-depth example of how to apply the adjustment factors. Step 1 is go to the URL under item A. This is the NOAA PDF server that was touched on during Module 1 in the Stormwater overview. Step 2 is to select the proper dropdowns for what we want. The data type should be precipitation depth, and the units should be English, and the time series type should be partial duration. Step 3 is to select location. You can do this by coordinates, station, or address. Because we are looking for Trenton Station 2, we'll select that from the station dropdown. Step 4 is to locate the 2, 10, and 100-year depths for the 24-hour storm, as found on the screen in red boxes. You can do this by scrolling down the web page and selecting the PF tabular option under the precipitation frequency estimates. And then step 5, the last step, is to apply the adjustment factors from table 5-5 of 7:8. This site is located in one county, Mercer County, and we're looking for the current adjusted rainfall. So we'll just need to apply the current adjustment factors for Mercer County. For example, for the 2-year storm, the depth from NOAA is 3.33 inches, and the current adjustment factor from 7:8 is 1.01. Multiplying these together, we get 3.36 inches. The same process should then be repeated for the 10-year storm and the 100-year storm. Please note that Chapter 5 of the BMP manual provides even more guidance on how to use the NOAA PDF server. Moving on to goal number 5, we're going to talk about unconnected impervious cover and how to use the NJDEP two-step method to calculate the runoff volume for a site. So what exactly is unconnected impervious cover? Unconnected impervious area means that stormwater runoff travels as sheet flow onto an adjacent pervious area, along with meeting some other requirements, before reaching the downgradient BMP. Essentially, the impervious area is not directly connected to the BMP. And the two graphics on this slide illustrate that scenario. Like the slide says, by providing the right conditions, this technique can encourage infiltration, address water quality, and reduce the volume of runoff. So what are those conditions? There are 5 conditions that must be met for an impervious area to be considered unconnected impervious area. Here are the first 2 conditions, and please take a moment to read the slide. Basically, the runoff must enter the pervious area as sheet flow and remain that way. And the last 3 conditions basically ensure stability and maintain sheet flow. So again, I'll just give a moment for the slide to be read. So for this reason, the maximum slope of downgradient pervious areas is 8%. There are 2 methods that may be used to calculate runoff from unconnected impervious areas, and there are 3 additional requirements applicable to either method. So the first requirement, only the portions of the impervious surface and downgradient pervious surface on which sheet flow occurs can be considered in this calculation. Number 2, the maximum sheet flow length along the impervious surface is 100 feet. And then lastly, number 3, the minimum sheet flow length along the pervious surface is 25 feet. The 2 methods to calculate runoff from unconnected impervious areas are the NRCS composite CN with unconnected impervious area method, and that's from Chapter 9 of the NEH and has a 30% limitation on the ratio of impervious area to total area. And then the other method is the NJDEP two-step method, which we will cover now. So let's get right into this example. So in this example, we have a 25-foot impervious area, which meets the 100-foot maximum requirement, and a 75-foot downgradient pervious area, which meets the 25-foot minimum. The impervious area has a CN of 98, and the pervious area has a CN of 39. The 2-year design storm depth is 3.5 inches. And we're going to ignore adjustment factors for the purpose of this example. We'll just assume that it's already been adjusted. The first step is to compute the runoff from the impervious area. And to do that, we will use the CN runoff equation that we talked about in the beginning of this presentation. Plugging in the P2 value and the CN value, we get 3.27 inches. And multiplying that by the surface area, which is 200 feet by 25 feet, we get 1,362.5 cubic feet. The next step is to convert the runoff from the impervious surface to a hypothetical rainfall depth over the pervious area. And we'll do this by back calculating a P2I value using the surface area of the pervious area and converting units as needed. And so for that, we get 1.09 inches. We then have to add this 1.09 inches to the depth that is falling directly on the pervious area for a total effective depth of 4.59 inches. So basically, adding the typical rainfall depth plus what is coming from the impervious surface. Now, using the CN runoff equation again, we can calculate the total effective runoff depth using this 4.59 inches, and we get 0.125 inches. And then lastly, converting this runoff depth to a runoff volume, we get 156 cubic feet, which is a massive decrease from over 1,300 cubic feet. Moving on to our last goal, goal number 6, we're going to talk about conditions for using exfiltration in runoff calculations. So before we dive in, let's talk about what it even means to use exfiltration in runoff calculations. It means that you are proposing an infiltration BMP, and you want to account for the decrease in volume that comes from infiltrating whatever amount of water you are proposing to infiltrate. In order to do that, there are some conditions that you have to follow. So here are the first requirements for using exfiltration in routing calculations, as listed on pages 7 and 8 in Chapter 5 of the BMP Manual. Generally speaking, exfiltration is only allowed for certain small-scale GI BMPs that infiltrate runoff. Additionally, all soil testing must follow Chapter 12 requirements, which will be further discussed in the next presentation. All design criteria, as provided in the respective chapter of the BMP Manual, must be followed. And pre-treatment must be incorporated, unless specifically stated otherwise in the BMP Manual. An exception would be for BMPs whose contributory drainage area is less than 1 acre. So let's talk a little bit more about pre-treatment. Because that requirement extends beyond just using exfiltration in the routing calculations. Pre-treatment is an important design criteria for all BMPs. And if you do not see pre-treatment listed under the basic design criteria for a particular BMP, it's under the type-specific design criteria. So starting with roof runoff can be pre-treated by certain measures listed here and on the pages listed in the bulleted text. And here are some graphics taken from Chapter 9.1 showing the devices that can be used to pre-treat roof runoff. We have leaf screens, first flush diverters, and roof washers. However, the requirement for pre-treatment of roof runoff can be waived under the conditions listed here. For example, a building that is significantly higher than any surrounding trees and does not have a vegetated roof should not need the pre-treatment. However, in making this determination, the review agency must consider the mature height of any surrounding trees. And this waiver does not apply if the roof runoff commingles with other stormwater runoff. Now, when using another BMP for pretreatment, it must be designed in accordance with the design requirements outlined in its respective chapter. Always check the BMP manual for specifics. For example, for subsurface infiltration basins, pretreatment may consist of any of the BMPs found in the manual, and 80% TSS removal by the pretreatment is required. But for small-scale bioretention systems designed to infiltrate that have flow entering as sheet or overland flow, they may alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of the other forms of pretreatment. Now back to the requirements for using exfiltration. Where can't you use exfiltration? Exfiltration cannot be used with any underdrained BMPs because the entire premise of exfiltration is infiltration, and with underdrains you are not infiltrating. Additionally, exfiltration cannot be used for the entire 2, 10, or 100-year current and/or projected storms, except under certain conditions listed here. For example, if you have no runoff leaving the site in pre-construction conditions, you can exfiltrate that entire storm in the post-construction conditions. Additionally, another review agency, such as the Pinelands, may require storms larger than the water quality design storm to be infiltrated. In addition to this, the soils must be tested in accordance with Chapter 12 of the BMP Manual, and the groundwater mounding analysis must be completed in accordance with Chapter 13 to ensure no adverse impacts to the groundwater or surrounding structures. And an important note when using exfiltration in your routing calculations, the groundwater mounding analysis must use the maximum amount of volume to be discarded during any of the storms to compute the duration of infiltration period. And here are some additional things you need to know about groundwater mounding. The groundwater mounding analysis has determined that an adverse impact will occur if the resulting groundwater mound reaches the bottom surface of the BMP, or if the temporary localized increase in the water table encroaches upon a building or another structure, including any septic systems. When an adverse impact is the result, further modifications to the size of the infiltration area of the BMP or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. A groundwater mound that reaches the bottom surface of the BMP means that the hydraulic gradient is reduced, which is another way of saying that the BMP cannot infiltrate runoff as fast as originally expected. So you will have to redo the routing calculations to calculate new peak flow rates. And as noted on the bottom of this slide, if adverse impacts cannot be avoided, the infiltration BMP cannot be used. Now, I know that was a lot of words, a lot of everything, but thankfully we have a whole presentation on groundwater mounding in Module 4, including examples. So don't worry. And all you need to know for now is if you want to use exfiltration in your routing calculations, the groundwater mounding analysis becomes even more important. And that's the end of this presentation. So I would like to thank everyone for your attention. And if you have any questions in regard to stormwater calculations, please feel free to reach out to the group or to myself, and my email is on the screen. Now, before we wrap up this portion of the presentation, if you have any questions, please add them to the chat. And I will check in with Lisa now. It seems we might be taking a break, Lisa.
Yes, I see that it's 2:21 p.m. Please come back in 10 minutes and we will start with the soil testing presentation. Thanks, everyone. We appreciate your being here.
All right. Thanks, everyone. See you all in 10 minutes.
Okay, it's 2:31. Welcome back, everyone, from your break. I'm Lisa Schaefer. I'll be presenting the soil testing requirements. So Chapter 12 was last updated in March of 2024, but I still see people referring it as, or to it as Appendix E, which is the name of the even older version. So please be sure to use the latest version in which some of the links were updated along with some of the content. As part of our audit experience, soil testing has been one of the areas that we often find was not done correctly. And it's absolutely crucial to the design of stormwater BMPs that are intended to meet the requirements of the stormwater management rules that we understand the characteristics and also the saturated hydraulic conductivity of surface and subsurface soils at the site. I'll be going over the soil testing requirements and what is to be submitted with regard to soil testing in your stormwater management report for a major development project. So this presentation will cover the information that is also in Chapter 12, and that includes why we need soil testing, testing for hydrologic soil group determination, testing to determine the location of the seasonal high water table, testing for our infiltration BMPs, soil testing requirements for construction and post-construction, and what information should be submitted in a soil testing report. So also covered in Chapter 12 is information pertaining to testing for the input parameters used in the groundwater mounding analyses. This information begins on page 29, and additional information is also found in Chapter 13. So Peter will cover groundwater mounding in further detail in Module 3. All right, so the identification of the correct hydrologic soil group is essential to performing accurate calculations for the volume and peak flow rate of runoff, regardless of the BMP being designed. Also, many BMPs require separation between the bottom of the BMP and the seasonal high water table. In a small scale infiltration basin, the 2-foot separation from the seasonal high water table is measured from the bottom of the sand layer. For a large-scale bioretention system with underdrain, page 11 of Chapter 10.1 specifies that the seasonal high water table must be at least 1 foot below the bottom of the bottom gravel layer. So all right, in that you have your underdrain, and that has to sit on at least 3 inches of gravel. So if there's no soil testing report showing the depth of the seasonal high water table, the reviewer will not be able to judge if this design criteria has been met. So also, when you're using the groundwater recharge spreadsheet to calculate annual groundwater recharge and the deficit, one needs to know not only the HSG, but the soil series. So details on this will also be covered in Module 3. Lastly, the saturated hydraulic conductivity, which generally speaking is the ability of a saturated soil to transmit water, is used in BMP design and for the input parameters in a groundwater mounding analysis. So we're going to take a look at all the requirements for all of these. Hold on. The first topic is the determination of HSG, which is used in the selection of the runoff curve number, or CN, developed by the NRCS, our Natural Resource Conservation Service. There's 3 methods to use to determine HSG. First is the web soil survey, and you have the link. Okay, you have the default method, and you have the HSG testing procedures from subsection 1C in Chapter 12. So before we go through each of these, let's talk about using those old ones. We checked with the NRCS and they indicated they're no longer updating those old paper documents. They also indicated that the web soil surveys are the most up to date in terms of information. So if you see someone still using the paper-based information, you're going to need to make sure it's verified with the web soil survey. So the web soil survey is the first source to be consulted for HSG information before going on to using the second and third method. All right. And we all should know by now that NRCS has soil maps and data for just about 95% of the nation's counties. So the web soil survey is fairly user-friendly, and that makes it great for checking the accuracy of the submitted information. However, if someone made a submission and they forgot to include it in their submittal, you can get it yourself and continue checking parameters without having to wait for them to get that to you. But there's more information on the steps in chapter 12 on using the web soil survey if you've never done it before. Okay, so once you're on the website, you're just going to click the start button. I'm going to give you the abbreviated version. Everything is in chapter 12. All right, you're going to define your area of interest, which is the AOI for short. And you're either going to do that by zooming into your project location or by entering the address. Then you're going to use either the polygon or rectangle option to draw your AOI around your site. I like to make them pretty close, and then I check them against the area, maybe on the cover sheet of the plans for the property in question. All right, so make sure your area is correct in size, and then you're going to look under the AOI properties pull down menu to see that. Next thing you're going to do is very simply go to the Soil Data Explorer tab. You're going to see this on the next slide, so just bear with me. And then you're going to go to the middle tab labeled Soil Properties and Qualities. And then there's a pull down menu that you'll see in just a moment, and you'll find your hydrologic soil group sub-menu. All right, but here's our example site. And the orangey outlines in the soil map are the individual soil mapping units. In case you don't know, soil mapping units are defined as a collection of areas defined and named the same in terms of their soil components, that is, series, or miscellaneous areas, or both. Note that each map unit differs in some respect from all others in a survey area and is uniquely identified on a soil map. So let's look on the next slide about getting that HSG information. All right, we're on the Soil Properties and Qualities tab, and on the left, we've expanded the Soil Qualities and Features menu to reveal the Hydrologic Soil Group submenu. When you select the View Rating button that's shown here with the arrow, the image on the right will change to look like what you see here with these colors and everything. All right, and then the table will open listing the HSG for the soils within the selected area, and they're listed by soil mapping unit. And this is the table down here. All right, the first row in the table, all right, is Fort Mott Loamy Sand, and it has a rating of A. All right, it covers the area shown over here on the right. Okay, the second is Galloway Loamy Sand, and we see right here a double rating in the table. So for the soils with dual HSG ratings, and those are AD, B/D, or C/D, the first letter applies to the drained condition and the second applies to the undrained condition. The appropriate choice of HSG depends on whether or not the site has been drained, and further investigation is needed. So we'll get to that in a little bit. All right, so moving down the table, down here where I've outlined in red, you're going to notice this little greenish gray rectangle that I added. All right, there's no ratings here. That's kind of why I wanted to call it out. These rows correspond to the two areas of the map that are also filled with that gray-green color inside the things I drew on top. Okay. A lack of rating often happens in urban areas where the soil might have been disturbed or the air has been filled with construction materials. And when there's no HSG rating, you will often see UR inside your AOI, and you'll get a message that the rating cannot be displayed. In this case, the soils in the undetermined HSG and soil series may be determined by the default method or the procedures identified in subsection 1C from chapter 12, both of which I'll get to in a moment. But if it's known that the site's been filled with construction materials, debris, or other material than this soil shown in the soil survey map, you may not solely rely on the HSG information shown here. The other methods will have to be used to determine the HSG. So where HSG information from the soil survey is unavailable, the next method is the default method. They're used for runoff computations for pre and post development conditions. So default values can be used often in urban areas where HSGs are not known, but you need to know if you're in the coastal plain or outside of it. So in the coastal plain, the pre-developed condition HSG that is to be used is A, all right, with HSGD used for the post-developed condition. Outside the coastal plain, you're using B for the pre-developed and D again for the post-developed. So, all right, you've seen this figure over here. It's 12-2 in the chapter, and that's a good general idea of where the coastal plain is found. But Peter showed us in the previous presentation on how to view the physiographic provinces of New Jersey on a department webpage. So here's that link again. All right, and that will take you to the Bureau of GIS for their interactive website. And you can now enter your location to find out in which province your address is located. So when it's zoomed out, when it first starts, this is what it looks like. Okay, the page is interactive, and you actually can zoom in enough to differentiate between two houses on the street. In fact, here's 401 East State Street next to the green arrow that I added, and we see that the site is in the Piedmont province. The lighter blue area on the bottom of the screen, all right, is the coastal plain. And I think you can appreciate how much easier it is now to figure out if something is in the coastal plain. All right, so you also need to know the HSGs on a site when using the groundwater recharge spreadsheet. And table 12-2 in the chapter was updated to show the default soil series for recharge computations. This table is on page 6 in the chapter, and then go to page 10 for the discussion. And we'll also cover this a little bit in module 3. So if you don't want to use the default HSG values, soil testing, all right, is used to identify the HSG. And these factors influence the hydrologic soil group, okay? All right, the third solid bullet is a quote from Chapter 7 of the NRCS National Engineering Handbook in Part 630 Hydrology. And its HSG assignment is determined by the water transmitting soil layer with the lowest saturated hydraulic conductivity and depth to any layer that is more or less water impermeable, such as fragipan or doripan, or depth at a water table if it's present. The least transmissive layer can be any soil horizon that transmits water at a slower rate relative to those horizons above or below it. For example, a layer having a saturated hydraulic conductivity of 1.3 inches per hour is the least transmissive layer in a soil if the layers above it and below it have a saturated hydraulic conductivity of 3.3 inches per hour. So use the link shown to view Chapter 7 of the NEH. And now let's look at Table 7-1 from that chapter, which relates saturated hydraulic conductivity to hydrologic soil group. All right, here's that table. So depth. HSG is determined by depth to a water impermeable soil layer that has a saturated hydraulic conductivity of 0.0014 inches per hour or less. It's also the depth to the seasonal high water table and the saturated hydraulic conductivity of the most restrictive soil layer within the depth to a water impermeable layer. So again, we have another quote. Certain wet soils are placed in group D based solely on the presence of a water table within 24 inches of the surface, even though the saturated hydraulic conductivity may be favorable for water transmission. If these soils can be adequately drained, then they're assigned to dual hydrologic soil groups, A/D, B/D, and C/D, based on their saturated hydraulic conductivity and the water table depth when drained. Okay, the first letter is the drain condition and the second is the undrained condition. So for the purpose of HSG, Adequately drained means that the seasonal high water table is kept at least 24 inches below the surface in the soil where it would be higher in a natural state. So in this table, the HSG designation is in the right-hand column. If the depth is less than 20 inches, okay, we're D, okay, per the top row. So where the depth to the water impermeable layer is 20 to 40 inches, we would look here by the red oval, all right? And if the depth to the high water table is less than 24 inches, we would look in the rows to the right of the orange oval. So that's where we find the appropriate saturated hydraulic conductivity range for the least transmissive layer within the corresponding depth range for the site conditions. Okay, now testing's rarely ever done at a single location. So you're going to have a number of tests to evaluate. So if, say, 7 of 8 soil explorations indicate that the depth of the seasonal high water table exceeds 24 inches, then a single anomalous result of less than 24 inches should be examined more closely before reclassifying the soil as HSGD. There could be a perched water table at that one location, or maybe something else. But if there's a restrictive layer at 40 inches, it alone is not an indicator of D soils. Pay attention to footnote number 2 regarding the high water table during any month. All right. The NEH says that for soils with a water impermeable layer at a depth between 20 and 40 inches, the saturated hydraulic conductivity in the least transmissive soil layer is less than or equal to 0.14 inches per hour. Also, take note of footnote number 1 for additional details. Okay, so now, continuing on with our testing procedures, the presence and depth of restrictions must be included in the soil logs for each soil profile pit and boring. On the left is a soil sample log showing the depth to the restrictive layer, and the seasonal high water table is here in blue. On the right is a shallow soil pit with a face that's been cleaned and prepped for the describing the soil profile. It's not in our area. It's actually from Alaska, where the permafrost was about 15 inches deep. Anyway, let's look at the required number of soil profile pits and soil borings that are required for soil testing that is performed to determine the hydrologic soil group. So for each soil mapping unit that is less than 0.5 acres, you will need 1 pit and 1 boring. For each soil mapping unit that is between 0.5 and 2 acres, 1 pit and 4 borings are required. And for each soil mapping unit that is greater than 2 acres, 1 pit plus 1 pit for each additional 2 acres, and 4 borings plus 2 more borings for each additional 2 acres are required. The placement of the soil profile pits and soil borings is also an important part of the requirement. Soil profile pits and borings should be completed at equidistant locations within the boundaries of the mapping unit to provide adequate characterization. So we have 2 examples here. For the pink area, which is 2 acres in size, we see 1 soil profile pit and 4 borings, and this configuration meets the placement requirements. Criteria. For the 6-acre area on the right that's in green, we see 3 pits and 8 borings. That's 1 soil profile pit and 4 borings for the first 2 acres, then 1 soil profile pit and 2 borings for each additional, and then we have the last one, right? This configuration also meets the placement requirements. There's also a depth requirement for determination of HSGs, all right? In the earlier version of this chapter, back when it was Appendix E, you had to go 6 feet. Chapter 12 has been changed. It requires at least 40 inches, okay? So the presence and depths of the soil classifications must be included in the soil logs. There's also an updated workbook for soil testing you can download from our website This link will allow you to select the Chapter 12 information corresponding to either the rules in effect on July 17th, 2023, or those in effect on January 20th, 2026. In either case, Chapter 12 was last updated in March of 2024, and for now, the two versions are the same. So if you open this up and you see tan or orange fill cells, you're in an older version. You want to see green and yellow. Okay, so what's shown here is the first worksheet, which is also figure 12-3 in the chapter. And you're going to enter in the top part the size of each mapping unit, and then the spreadsheet will calculate the number of soil profile pits and also the number of soil borings required. All right, and then you'll see the results displayed wherever there is a yellow fill color. The lower part, okay, can be used to calculate the depth of a soil profile pit or boring. And based on the information entered, in the event the seasonal high water table is within 24 inches, a message will be displayed indicating that there are HSGD soils present. Okay. Next, we're going to look at the requirements for soil testing to determine the location of the seasonal high water table, and that information is found in Chapter 12 in subsection 1D. So, pursuant to Table 5-1 in the rules, testing for seasonal high water table is not applicable for BMPs such as blue and green roofs as they're constructed above grade. All right. Plus, the others where no separation is listed in this table. All right. You're going to take note that testing to determine the location of the seasonal high water table is required for BMPs with underdrains, for grass swales, and of course, as can be expected, BMPs designed to infiltrate. The section of the chapter never stated that underdrain BMPs were excluded, so that's why we're clarifying this issue. Okay, so for BMPs designed to infiltrate, you're going to follow the guidance for determining saturated hydraulic conductivity and test at least 2 areas within the footprint, that is the bottom area where infiltration will occur. And for your non-infiltration BMPs, you're going to test within the area to be occupied by the BMP, and then the number of tests that are required follow the same requirements for those of an infiltration BMP. All right, so take note that subsection 2B in Chapter 12 covers the soil testing for non-infiltration BMPs that have a required separation from the seasonal high water table. And we're going to go to the testing for infiltration BMPs in just a few minutes. But if you're getting inconsistent results in your tests, or you as a reviewer are seeing such inconsistencies, then you're going to either perform if you're doing the tests or require more tests if you're reviewing, whatever the case applies to you. And for you visual learners like me, the next is a graphic to illustrate when certain testing and resource data may be used to determine the seasonal high water table. All right, timing is everything when testing to determine the location of the seasonal high water table. All right, this slide should clarify some misunderstandings about when to perform testing for this purpose. So subsection 1D in the chapter was updated with the March 2024 version to further clarify this. So when you set out to determine the location of the seasonal high water table, there's a sharp divide in how you determine where it's located. And this is based on the features you see depending on the time of year the exploration is made. All right, so the next few slides will fill in the details in this graphic, okay? And this is found in Chapter 12 and it begins on page 11. We're going to start with the simple case, all right? What applies when the answer to the question, all right, of whether modeling is observed is yes. So where modeling showing redoxomorphic features is observed at any time of the year, the seasonal high water table, is taken at the highest level at which the redoxomorphic features are observed, except when the water table is observed at a level higher than the level of the redoxomorphic depletions or concentrations. So if the water table is higher in elevation, then those features use the higher elevation. On the other hand, if the water table is located at a lower elevation or if no water is observed within the exploration, use the elevation of the modeling showing redoxomorphic features as the location of the seasonal high water table. For details on determining whether saturated soils are present, there's a guidance document. It's published by the NRCS. It's called Field Indicators of Hydric Soils in the United States, and you can use it. Okay? All right. So for item 2 in the citation, which applies where modeling showing redoxomorphic features is not observed. So then the seasonal high water table is determined as follows. Okay, where A corresponds to the yellow shaded part of the arrow and B to the arrow with the red fill. So during the months of January through April inclusive, water levels may be measured directly within soil profile pits or borings. Now, when the department determines that there's been a significant departure from normal climatic conditions, the department may, with due notice to the administrative authority, lengthen or shorten the period allowed for direct measurement during any given year. In low-lying coastal areas where the groundwater fluctuates with the tides, measurements shall be taken at the time of highest groundwater elevation in response to tidal fluctuation. But I want you to take note that there's been no change in the time frame for direct observation as long as I can remember. All right, now, during other times of the year, the depth of the seasonal high water table is obtained from the Web Soil Survey, provided that the soil series present at the site is identified based upon comparison of soil profile morphology observed within a soil profile pit and the soil profile description provided for the soil series in question within the NRCS Web Soil Survey. So where the seasonal high water table is shown as a range of elevations in the Web Soil Survey, the highest elevation is what is used as the seasonal high water table. So this is the complete graphic for your use. All right, so if you're performing your exploration in August and a redoxomorphic feature is observed, that's where the seasonal high water table will be marked as located, unless, of course, the water table is actually higher. All right, however, for testing done outside of January through April, if you do not see redoxomorphic features, you follow the text in 7:8-5.82b, which stipulates a comparison of the soil profile morphology observed with the information in the Web Soil Survey is needed to identify the soil series present on the site. So for those of you who prefer text over graphics, Chapter 12 also has some really great tables, all right? 12-5 is the table that applies when modeling showing redoxomorphic features is observed within the soil exploration, and that's on page 12 of Chapter 12. All right, and 12-6 is where no observation of modeling showing redoxomorphic features and whether or not the water table is observed for the January through April timeframe. All right, for the rest of the year, all right, the soil profile observed in a profile pit is to be verified against the Web Soil Survey. All right, note these settings, all right, that should be shown or used in the Web Soil Survey. And lastly, down here, look down here, all right, if the soil profile from the profile pit is not verified against the info in the Web Soil Survey, the seasonal high water table is undetermined. All right, compliant testing, as stated in the right-hand column, is therefore required. All right, so we've got another worksheet for this, okay? And it's the third worksheet in the book. All right, and you'll find it also in Chapter 12 as figure 12-8 on page 26. And this is just the top part of the worksheet, all right, that you can use. There's a column for recording the soil morphological observations and one for other notes. A good soil log is going to include the hue, the value, and chroma observed to aid in the determination if redoxomorphic features are present. Okay, so we're going to move on to the soil testing requirements for BMPs designed to infiltrate. Okay. These are found in section 2 of chapter 12. First of all, by infiltration BMPs, we mean a BMP that infiltrates runoff into the subsoils, including BMPs such as infiltration basins, along with sand filters, bioretention basins, and pervious paving systems that are designed without under drains. All right, testing for BMPs with under drains was discussed on slide 16. All right, so let's look at the number of soil profile pits and soil boring requirements for any infiltration B. That's in subsection 2A of chapter 12, right? So knowing where seasonal high water table is essential. A minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP to determine the elevation of seasonal high water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the seasonal high water table. All right, and you've got to have the placement of the test pits be sufficient to provide adequate characterization of the infiltration area. But for BMPs with infiltration areas larger than 10,000 square feet, a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. And at least 1 test to establish the soil hydraulic conductivity must be conducted for each soil profile pit. All right. So when reviewing the plan, in order to verify the locations and number of soil profile pits, you need to see a site plan depicting the locations of those soil profile pits to make sure they're within the infiltration area of the proposed BMP. Of course, substitutions and proximity information are also found on page 17 of chapter 12. All right, a soil profile pit may be substituted by soil borings only when the conditions stated in the subsection titled Soil Boring and Profile Pit Locations and Allowable Substitutions, which begins on page 7, are fully met. The final location of a proposed BMP can differ from the location of a soil exploration. So as long as the proposed BMP is within the same soil mapping unit, a new soil exploration is not required under the following circumstances. If the soil explorations that have been performed are still within the infiltration area of the BMP at its new location, or if the new location of the BMP is within 25 feet in any direction of all of the original soil exploration locations. So just so you know, item 7 in subsection 2A also includes information on when additional soil profile pits may be required. You're going to see that on page 18 of chapter 12, and below it is a table of examples illustrating the number and type of soil explorations required for various types and sizes of BMPs. So speaking of examples, let's do one. All right, so we're going to look and determine the number of soil profile pits needed for an infiltration BMP with a bottom area measuring 100 feet by 200 feet and is 25,000 square feet in area. So for this infiltration basin, we need 2 profile pits for the first 10,000 square feet. All right, which since the basin is 100 feet wide, translate to 100 feet of length. All right, as marked. And then we're going to need 1 for the additional 10,000 square feet in the middle, plus 1 more for that extra 5,000 square feet at the end. All right, so the next few slides, we'll look at the number and location of tests for special types of infiltration BMPs. And then we'll look at the requirements for small scale and then linear BMPs. And then we'll go on to some other tests that we need to perform for all infiltration BMPs. All right, so for small scale infiltration BMPs, when we have 1 or more small scale GMPs, we need 1 soil profile pit for each soil mapping unit where the multiple BMPs are located. Okay, for each BMP with an infiltration area of less than 5,000 square feet, you're going to need 1 soil boring at each BMP. And then for those BMPs with an area that is greater than 5,000 square feet, You need 2 soil borings at each BMP, and for small scale GI BMPs that are arranged linearly, you will follow these requirements. All right. I wanted you to have it in a handout, but you'll find this on pages 15 and 16 of chapter 12. And that's, remember, under part of subsection 2A. All right. So for our linear infiltration BMPs, first off, to be a linear infiltration BMP, you have to meet all 3 of the bulleted criteria. Okay. And that's also listed on page 15 of chapter 12. All right. So for our linear infiltration BMPs, a minimum of 1 soil profile pit must be conducted within each soil mapping unit. In each soil mapping unit, the profile pits must be conducted within the first 500 linear feet of the BMP. Now, where the length of the linear BMP exceeds 500 linear feet, 1 soil boring must be conducted at every 500-foot interval, and then 1 additional soil profile pit must be conducted for every 2,000 linear feet. And all soil borings need to be equidistant to adequately characterize the infiltration area. Okay, let's do some examples. All right, we have 2 sites. All right, the first is this site that we have here on the top. All right, and this one has 2 soil mapping units. We must include 1 pit for a linear BMP 500 feet in length that's shown with the yellow shading. And then we need 1 pit for the first 500 linear feet for the soil mapping unit shaded in green. All right, with 1 boring for each additional 500 linear foot portion. So as long as the 2 pits and 3 borings are performed, this example meets the requirements. For the second example, this is a linear infiltration BMP with a total length of 2,500 feet, all within 1 soil mapping unit. So what is needed is the required pit for the first 500 linear feet, followed by 1 boring for each additional 500 feet increment, and 1 more pit for the additional 2,000 linear feet, located after the first. Okay, so these, all right, are found in figure 12-4 of the chapter. All right, so let's continue with the other soil tests needed for infiltration BMPs. All right, those are the tests to determine soil hydraulic conductivity, depending on whether or not soil replacement is proposed. So for no soil replacement, after determining the numbers and locations of the soil profile pit for infiltration BMPs, you have to decide the depth of the soil profile pit. And then there's the question of which soil layer do you select for performing the test for soil hydraulic conductivity. All right, so soil hydraulic conductivity testing must be conducted for the most hydraulically restrictive horizon or substratum above the seasonal high water table or non-fractured bedrock, but located below the lowest elevation of a BMP and above whichever of the following depths is greater: 8 feet below the lowest elevation of the BMP, or to a depth equal to twice the maximum potential water depth in the BMP measured from the lowest elevation of the BMP component thingies. All right, so from our audits, the depth to which the soil exploration extends to locate the most hydraulically restrictive layer is quite often too shallow. I've seen depths of 10 when we need 11, 12, or even 13 to meet the requirements. All right, and I just looked over a site for its soil testing, and the depth of the infiltration testing turned out to be 3 feet above the proposed surface elevation of the basin. So as the plans changed, the reviewer did not relate the information on the newest grading and utility plans back to the original testing that was done. Of course, it was many years prior, but this kind of approval can put the municipality in a precarious position. All right, but let's just move on. All right. If soil replacement is proposed beyond the required layers in a BMP, the depth is measured from the elevation of the bottom of the required sand or soil layer. Right? So this requirement means first, the excavation of the soil profile pit must reach to the required depth, and second, the hydraulic conductivity must be tested on the most hydraulically restrictive soil layer below the soil replacement or lowest point of the basin, but above the required soil profile depth. All right. Again, the depth requirement of whichever is greater, 8 feet or twice the maximum water depth, is measured from the lowest point of the basin bottom or from the bottom of the soil replacement, whichever is deeper. I mean, we've seen in our audits that the soil hydronic conductivity test is performed at the top of the soils to be replaced, but doesn't include the depth of the replacement. And that's just wrong. All right. Up next is a discussion of what test methods are acceptable for this type of soil testing, and you'll find this in section 3 of chapter 12. Soil hydraulic conductivity tests can be determined using a tube permeameter test, a percolation test, a single ring infiltration test, a basin flooding test, or a modified basin flooding test. But please read the specific conditions published in chapter 12 under which these tests can be used. Now, there's additional methods of establishing the soil hydraulic conductivity. That would be ASTM D3385, the double ring infiltrometer, and USBR 7300-89, well permeameter method, or other soil hydraulic conductivity tests that utilize in situ conditions and are accompanied by a recognized published source can be used. That would be like your Guelph permeameter, your Philip Dunn permeameter, and available at the Soil Science Society of America book series, number 5, Methods of Soil Analysis, Part 1, Physical and Mineralogical Methods by Clute, that dates back to 1986. But too often in our audits, we've seen that disturbed samples are used for lab testing. Please, in your reviews, make sure undisturbed soil sampling is performed for your soil boring explorations when used in any laboratory-based test. Additionally, when performing a soil boring during the soil exploration, the soil borings must be performed and reported in accordance with ASTM D1452, called the Practice for Soil Investigation and Sample Auger Borings, and ASTM D1586, Test Method for Penetration Tests and Split Barrel Sampling of Soils. Note that sampling must be continuous for the entire depth of the soil boring to fully characterize the soil profile. Since the actual saturated hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated hydraulic conductivity rate to determine the design saturated hydraulic conductivity rate. That's what's then used to compute a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowed to use exfiltration in routing calculations, or the recharge rate in the groundwater mounding analysis. So where any tested hydraulic conductivity rate is 20 inches per hour or more, the maximum design saturated hydraulic conductivity rate that can be used is 10 inches per hour. All right, so the test procedures and conversion equations for the test shown are available in Chapter 12, and there's also worksheets for some of these. So you're going to see them here, and this is what page to look at them. Pretty straightforward. However, the cased borehole infiltration test was previously suspended for further assessment. The ASTM standard for this test indicates it's not suitable for cohesionless soils, and upon closer review, the soils for which this test would be appropriate would have saturated hydraulic conductivity ratings below the minimum permitted for an infiltration BMP, and as a result, this test has been removed from Chapter 12. Okay, but for your double ring infiltrometer, your well permeameter, and the other permitted testing results, you're going to get them from the American Society for Testing and Materials, or the organization that published the testing method. All right, for the percolation test, you're going to follow the procedures described in Chapter 12. All right, but the field measured hydraulic conductivity value is calculated using this simplified equation. All right, it's in the chapter. All right, in case you don't have your handouts handy. All right, but you want to take note that although the test step B in the procedure for the perk test requires you to fill the water to a depth of 7 inches, the time of recording is started when the water level drops down to the 6-inch mark, measured from, all right, and stop when the water in the hole is empty. So you've got that extra 1 inch. All right. So the second worksheet in that Excel workbook I talked about may be helpful for your hydraulic conductivity testing. All right. On the left is the top and middle. On the right is the other part. All right. So you've got the number of profile pits and borings required depending upon the type and size of the BMP. And then this is your depth of testing. All right, so again, the title has changed and the fill colors indicating green and yellow represent the newer version of Chapter 12. All right, so Section 4 of Chapter 12 is the construction and post-construction testing requirements. All right, so regular oversight must be provided by the professional engineer to establish that the basin will function as designed. Oversight includes, but is not limited to, a pre-construction meeting with the contractor, confirmation of the proper use of construction equipment, especially to minimize compaction of the infiltration area, ensuring that the earthwork does not occur within the BMP area when the soil moisture content is above the lower plastic limit, and that the specifications of any replacement soils are met. You're also going to want to ensure that proper precautions are taken to prevent sediment entering the infiltration area during construction. And if that's unavoidable, if the basin is used as a sedimentation basin, excavation for the sediment basin is at least 2 feet above the final design elevation of the basin bottom. Okay, so post-construction soil hydraulic conductivity tests must be conducted to ensure that the installed BMPs function as designed. It's part of the design criteria, all right, in the BMP manual. Such tests must be carefully undertaken when all BMP construction that may affect soil hydraulic conductivity has been completed. So that includes the use of construction equipment and the placement of construction material that could potentially affect soil hydraulic conductivity. So hand tools and manual permeability test procedures must be used to avoid affecting the soil hydraulic conductivity. And the required number of tests for post-construction tests are as followed. All right. The number of the tests must follow the same requirements as those for the pre-construction soil hydraulic conductivity tests. And as for the required test depth, the post-construction hydraulic conductivity test must be conducted at the bottom of the excavation of the BMP before the sand layer or soil bed is placed into the BMP. Okay, so the permitted test methods for post-construction testing are as follows. All right, only the single ring infiltration test, the modified basin flooding test, and the double ring infiltration test or similar tests that does not require a test hole in the soil layer are allowed. The tested soil hydraulic conductivity from the post-construction hydraulic conductivity test must be equal or greater than the tested soil hydraulic conductivity of the most restrictive soil layer that was tested in the pre-construction condition. And lastly, all post-construction soil hydraulic conductivity test results must be certified by a licensed professional engineer, submitted to the review agency, and then recorded in the as-built documents. All right, your review would include a check that these requirements are met. Okay, so yes, the slide is blank for now. I've covered the requirements for the soil testing, and that will provide information on the hydrologic soil group that determines the runoff from the site, for the saturated hydraulic conductivity that determines the permeability of the soil underneath the basin, and for the seasonal high water table that determines if the BMP can be drained at all. So therefore, I hope you'll agree that the soil testing results are an essential part of the stormwater management design. Okay, so also exfiltration is allowed in routing calculations for infiltration BMPs. And the volume and flow rate of runoff that can be actually infiltrated into the subsoil will affect the sizing of the BMP and the outlet structures. So more than ever, soil testing results that correctly describe the soil characteristics are really, really important. So let's address what's required for submittal with the stormwater management report. All right. The reviewer should check that the following is submitted. You've got a web soil survey showing your HSG, your locations of your profiles and borings, your soil logs that include the date, the elevation of the existing ground level, depth of the profile or boring, your classifications and descriptions, the depth of the soil, where the saturated soil hydraulic conductivity test is performed, and your observations of soil modeling or groundwater observation, and of course your hydraulic conductivity test results. All right, so that's pretty much everything I have for soil testing. So to recap, why we need soil testing was covered, soil testing for HSG, infiltration and BMP required testing, locating the seasonal high water table, soil testing requirements for construction and post-construction, and what information to submit in your soil testing report. So as a reviewer, you have to check this information. Please examine it, all right? Because many of the soil reports we've seen in our audits indicate incorrect or inaccurate testing took place, or there was incomplete information provided, all right? Remember, testing that is accurate is required in order for a BMP to merit the TSS removal rate listed in the tables of BMPs that may be used to address the water quality standard. The model SCO also includes language that testing must follow Chapter 12. So approval of a project for being compliant with the SCO is incumbent upon correct testing. So as a reviewer, you've got to check each and every part of the testing information for accuracy, since all of it influences the BMP design. And then the design examples you'll see in Module 4 will include these checks. All right, so we're going to go from this directly into the next thing because I see what time it is. All right, I know I talk long. Sorry about that. All right, so give me a second. All right, so GI fact sheet. All right, in earlier models, my colleagues introduced what we mean by green infrastructure and some of the regulatory requirements pertaining to it. So we're going to start with this review of this fact sheet thingy to help you better understand the rule requirements and how to use the fact sheet as a rubric to gauge whether or not BMPs that are proposed are being properly implemented to meet the GI requirements. And there are a few short examples that are also in the fact sheet that I'm going to cover. All right, so these are the topics I'll cover in the presentation, so let's dive in. All right, to get right to the first question, we covered in Module 1 what we mean by green infrastructure. Obviously, we abbreviate that as GI. And even NJ Cat spoke about GI MTDs, and we'll have more about GI in later modules. Remember, GI is intended to mimic natural hydrology, which is why a GI BMP is a stormwater management measure that manages stormwater close to its source by 1, treating stormwater runoff through infiltration into subsoil, 2, treating stormwater runoff through filtration by vegetation or soil, or 3, storing stormwater runoff for reuse. There's also some co-benefits to using GI, and they include a reduction in the urban heat island effect, decreased energy use, removal of pollutants from the air through greater utilization of vegetation, beautification of public spaces, and increased property values. So the fact sheet was created to help the public better understand that GI is very important for managing stormwater in that these BMPs more effectively maintain or mimic natural hydrology and provide environmental benefits by infiltrating precipitation to replenish groundwater and stream-based flow, evapotranspiring and evaporating precipitation to reduce stormwater discharge volume, and intercepting precipitation to reduce runoff and erosion. So where do we find the GI fact sheet? Well, a little over 3 years ago, our njstormwater.org homepage was updated to its new format. And please note, we're retiring that URL, all right? Please instead use this green link that is shown here, right? Put that in your favorites, all right? And to find the GI fact sheet, go to the lower right-hand corner above the blue bar, all right? And it's a PDF, download it. All right, so you could also just go to the link that's on the top of your slides, all right? It's just 8 pages, all right? It represents the information in the stormwater management rules, which if I say the rules, that's what I'm talking about. All right, this is just a screenshot of the top of page 1. And we're going to look at what's in the fact sheet. But first, we need to look at what the rules say about GI. In the rules, we find this requirement where underlined in red on the screenshot of the rules. The yellow highlighted area right above the red, all right, is where it says the design and performance standards for groundwater recharge, water quality, and quantity control must be met using GI. All right, it's under item F in this subchapter where you're going to find those tables 5.1, 5.2, and 5.3, and those tables list the BMPs and identifies whether they're 1, GI, or 2, GI requiring a waiver or variance if used for other than quantity control, or 3 as non-GI BMPs. And this was covered in Module 1 in the overview presentation. All right, but note that the tables themselves have important notes and footnotes that should not be underlooked. Of course, if you need help understanding them, please contact us. All right, the takeaway from all of this is that, first of all, the rules require a project meet the design and performance standards using GI. So that means usually Table 1 BMPs will be used as they satisfy all of the requirements. Table 2 BMPs, as covered earlier, can be used to address stormwater runoff quantity control. But when used for the other design and performance standards, the Table 2 BMPs require a waiver or variance, and Manesh will cover a brief refresher on variances in Module 3. Now, Table 3 BMPs are not GI, and they will also require a waiver or variance to meet any of the design and performance standards. All right, so that brings us to the end of item 2 on this slide, which says GI is to be used in accordance with subchapter 5.3, which we'll discuss next. All right, so subsection 5.3 in the rules is where we identify which of the GI BMPs have fixed contributory drainage area limits, and a contributory drainage area is defined in the rules as the area that drains to the stormwater measure, excluding the area of the measure itself. On the fact sheet below the first paragraph on page 1, these limits are restated. Take note that the GI BMPs found in Chapter 9 of the BMP manual that aren't listed here already have one or more design components that limit the size of the contributory drainage area. So, for example, grass swales have geometric constraints and a maximum depth of flow limitation of 2 inches. And the design criteria will impact how much area can drain to a given grass swale. All right, so next is how to implement GI into a project or make sure it has been properly implemented. All right, so the GI fact sheet is a metric to help you evaluate if a proposed BMP has been properly implemented where the rules require GI infrastructure, I'm sorry, green infrastructure be used. So what I'm saying is that the reviewer needs to make sure that each BMP proposed as GI is to check to see if it really meets the definition of GI that's in the rules. So that means all three of the questions shown here must all be answered with a yes in order for a BMP to meet the GI rule requirement. All right, so all of the GI BMPs proposed must each be reviewed to make sure that the project completes with the rule requirement to use GI. So let's go through these questions individually. So GI manages stormwater close to its source. Well, what do we mean by that? GI mimics the natural hydrologic cycle. So although stormwater traveling from this point, okay, on the right has a lot farther to go than a drop following over here has to go to get to the basin. Remember, clearing, grading, and paving results in much shorter values that are calculated for your runoff travel times because pavement is much smoother than natural terrain. Plus, we typically use uniform and flatter slopes for parking lots. Okay, so we can no longer direct runoff to a solitary basin. There should be more opportunities to treat runoff on the right side of this site in keeping with the pre-construction drainage conditions. The basin is not close enough to the runoff generated by the far right of the proposed parking lot. And also, there's little opportunity for stormwater to interact with vegetation or soil in this particular layout. So in conclusion, this layout is not GI. All right, so now imagine an old factory on a fully paved site in an urban area. Runoff from the roof drain to the parking lot and then to the street. All right, so that type of situation is described for this proposed urban redevelopment. All right, a fully impervious 3-acre site on an urban redevelopment area is proposed for redevelopment, and it will consist of a 1-acre building plus 40,000 square feet of parking areas and internal driveways. Also, a 1-acre overflow parking area. A green roof and an underground cistern are proposed to manage the rooftop runoff from the 1-acre building. Also, stormwater islands designed to infiltrate into the subsoil are proposed to manage runoff from some of the parking areas and the internal driveways. And a permeable asphalt system designed to infiltrate into the subsoil is proposed to manage runoff from the overflow parking area. So that's kind of what this would look like. The proposed redevelopment is a major development since it will disturb 1 or more acres and it's subject to the design and performance standards in the rules. However, because it's an urban redevelopment area and was completely previously disturbed and was fully impervious, groundwater recharge is not needed for this case. Now, the proposed condition also reduces the impervious surface for motor vehicles present on the site, all right? But this profile, all right, is what we mean by placing BMPs close to the source of runoff. So this is the plan view of the site we just saw in the profile. Since the existing site was so highly impervious, many of the non-structural stormwater management strategies that were required by the local MSWMP could not be easily implemented on the site. However, due to the proposed GI practices, the project does break up or disconnect flow of runoff over impervious surfaces and provides low maintenance landscaping that encourages retention and planting of native vegetation and minimizes the use of lawns, fertilizers, and pesticides. So in this example, each of the proposed GIBMPs manage the stormwater runoff generated by the redevelopment close to the source. So yeah, we can answer unequivocally yes to the first question on the fact sheet. The next question to be asked is if the GIBMPs are dispersed throughout the site. So the last site was a good example. All right, here's another. The parking stalls are the lighter gray
They're pervious pavement. They're separated by impervious aisles. Okay. And those aisles are graded to direct runoff to the pervious areas. All right. Roof runoff also drains to the storage beds below the pervious pavement systems. Okay. Without exceeding the drainage area limits. So, yeah, we can answer yes for this project as well. Now, 1 second. All right, this one's a beaut. This is our third site, and the requirement to distribute GI throughout the site does not mean that multiple GI BMPs cannot be near each other. All right, they need to be close to the source of runoff, and these dry wells are close to the building for which they manage the runoff, and they're distributed. They're on 3 sides, okay? Now, if this is part of a larger site where there are additional GI BMPs, this layout's fine, and a separate discharge for each of the 7 dry wells is not necessary. Note that as long as no more than 1 acre of runoff is directed to any individual dry well, the drainage area limitations are met, okay? But to BGI, they must each function individually for the water quality and the recharge storms. All right, so here's another example. The small-scale GI BMPs are all separated by berms and have contributory drainage areas below the maximum. However, they're all shoved over here in the corner. All right, look how far the building is from this cluster. Plus, there's nothing for stormwater over here. So the BMPs are not near all of the sources of runoff. So in conclusion, this design does not meet the definition of GI and therefore does not meet the rules. All right, last question that we have to ask and answer is whether the contributory drainage area of the proposed GIBMP is less than or equal to the limitation found on the cover page of the fact sheet. And again, it's in the rules at 7:8-5.3. Small-scale bioretention basins are ideal for use in parking lot islands and where one has typically used in the past that grass strip along the edge of a parking lot or along a roadway. Now, the drainage area limit for this type of BMP is 2.5 acres, and that's generally more than enough for these micro installations, okay? So GI has a special meaning in stormwater management. Again, it's a stormwater management measure that manages stormwater close to its source by treating runoff through infiltration into subsoil, treating stormwater runoff through filtration by vegetation or soil, or storing stormwater runoff for reuse. Okay, to address water quality, groundwater recharge, and runoff quantity control, the rules require GI be used, and by that I mean used correctly. So answering 3 questions when you review a design will check if GI is properly implemented on the site, meaning the GI BMPs are located close to the source of runoff, they're dispersed throughout the site, and that the drainage area limitations are met. So in Module 4, you'll have some examples, and we'll see if they do or do not answer any of the questions from the fact sheet with a yes. All right, so please use the fact sheet when performing your reviews of GI projects. All right, so thanks. I need can take your questions if you want to email them here. Of course, you can put them in the chat. You can also contact the unit. And I want to thank you. All right, so it's time for quiz 2. And so Peter's going to take over to administer the quiz. And thank you, everybody, for your attention.
Thank you, Lisa. I will now share my screen. All right, so as Lisa said, it is now time for quiz number 2. As noted before, it is important to complete the quiz now during the time allotted. Note that you cannot move forward to complete a quiz or complete a quiz at a later time. and we need the quizzes to be completed in order to issue credit for the class. So let's get to the quiz. So just like Tuesday, there are a few ways to get to the quiz. Note that if you access the quiz on the same device that's being used for this meeting, make sure to use a separate tab or browser so you are not removed from the meeting. The link at the top of this slide will take you to a page on our website, which includes the handouts as well as each of the quiz links. You can click the link for Quiz 2 found at the bottom of the web page to be taken to the quiz in SurveyMonkey. Another way is using the link at the bottom of this slide, which will also be posted in the chat, to be taken directly to the quiz in SurveyMonkey. Lastly, if you want to take the quiz on your phone, you can scan the QR code on this slide, which is also in the chat, and you'll be taken right to the quiz. And just a few other notes on the quiz. You must answer every question before you can advance to the next screen and finally submit. You may only take the quiz once, and we're going to allow 10 minutes to take the quiz. So it's now 3:41, so we'll give until 3:52 to take the quiz. So please aim to finish by 3:52, and if you finish early, you can feel free to take a short break. After this time, we will review the answers to each question from the quiz. The review portion of the quiz is part of the course and for credit and attendance, so please do not leave after completing the quiz. We won't keep you for too long. All right, so here's everything all in one place. Please begin taking the quiz, and I'll be back at 3:52 for the quiz review. Thank you. All right, welcome back, everyone. It's now 3:52, so I'm going to start the review. I will say, if you're not quite finished the quiz yet, you can continue to work on it as I begin the review. So the first 3 questions on the quiz were general information type questions. So we will begin at question number 4. True or false? There is no longer a minimum or default value that can be used for time of concentration using the NRCS methodology, meaning this value must always be calculated. And this statement is true. There is no longer a minimum or default value that may be used for the time of concentration. Time of concentration, or T sub C, for pre- and post-construction conditions must be calculated based on the flow path. Question 5. According to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used in sheet flow calculations for wooded conditions in New Jersey? The correct answer is 0.4. The maximum roughness coefficient that can be used for wooded conditions is 0.4. Though the National Engineering Handbook lists Manning's roughness coefficients as high as 0.8 for woods with dense underbrush, for New Jersey, the maximum roughness coefficient for sheet flow that may be used is 0.4. New Jersey does not contain land cover that supports the use of roughness coefficients associated with woods with dense underbrush. Question 6. What is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? The correct answer for this one is 100 feet. For the pre-construction condition, the maximum distance for which we can assume sheet flow occurs is 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale, curb, or inlet, to prevent sheet flow from occurring. And remember to use the actual distance if it's less than 100 feet. So this comes from Chapter 5 of the BMP manual, if you have not taken a look at that yet. Okay, question 7. According to the stormwater management rules, which methodology can be used in the computation of stormwater runoff? The correct answer is A, NRCS method. As of July 17, 2023, the stormwater management rules removed the rational method and modified rational method from NJC 7:8 5.7, and only the NRCS method is to be used in stormwater computations. Number 8, true or false? When using the NRCS methodology for directly connected impervious cover, averaging pervious and impervious curve numbers is permitted for calculating a hydrograph. This statement is false. Here's a quote from NJC 7:8 5.7A4. In computing stormwater runoff from all design storms, the design engineer shall consider the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces separately to accurately compute the rates and volume of stormwater runoff from the site. This statement does not apply when using the NRCS composite CN with unconnected impervious area method. See Chapter 5 of the BMP manual for more information. Number 9. When determining the curve numbers for site design, the design engineer should assume that the condition of the existing cover is good condition is the correct answer. This is fairly straightforward. Pre-construction condition curve numbers should assume that vegetated areas are in good condition. Number 10. Yes or no? Can the Delmarva dimensionless unit hydrograph be used for the redevelopment of a 2-acre entirely impervious site located within the coastal plain? The answer to this is no. The Delmarva dimensionless unit hydrograph must be used when modeling watersheds within the coastal plain region of New Jersey, with just a few exceptions. It cannot be used to size a manufactured treatment device, or MTD, as it may underestimate the peak flow rate entering the MTD. Also, for an entirely paved site, the significant surface storage associated with the coastal plain is no longer present, also resulting in underestimated peak flow rates if the Delmarva is used. Additionally, the Delmarva should only be used in areas that have an average watershed slope less than 5%. If any of these situations are proven to be present, the SES standard dimensionless unit hydrograph must be used. And a side note on this subject, if the Delmarva is used in the pre-construction condition, it must also be used in the post-construction condition. Same idea goes for the SES. Question 11, true or false? When using the NRCS methodology for calculation of stormwater runoff, the type 3 distribution must be used for developments in New Jersey. And this one is false. As discussed in the calculations presentation from today, NOAA C or D distributions must be used, not the type 3. Question 12, true or false? Pre-treatment must be incorporated into the design of a small-scale GIBMP that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. This one is true. All small-scale GIBMPs, which are designed to infiltrate into the subsoil and have contributory drainage areas greater than 1 acre, must include pre-treatment of stormwater runoff when using exfiltration in the routing calculations. Question 13. Soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? And the correct answer is all of the above. They all have a minimum separation from the seasonal high water table, which you can find in their respective BMP manual chapter. Soil testing will therefore be required for all of these to ensure that they meet the required separation. Question 14, true or false? A factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate, which is used for infiltration BMP calculations. And the correct answer is true. Since the actual saturated soil hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate. Computing a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowing exfiltration in the routing calculation, or the infiltration rate in the groundwater mounting analysis must all use the design saturated soil hydraulic conductivity rate. Number 15, yes or no? During the month of July, can the seasonal high water table be determined by measuring water levels directly within a soil exploration if the modeling does not indicate redoxymorphic features are present within the soil exploration? And the answer is no. If modeling does not indicate redoxymorphic features are present within the soil exploration, the seasonal high water table may be determined via direct observation of water levels only between January and April. For more information on determining the seasonal high water table, see subsection 1D of Chapter 12 of the BMP manual. Number 16, when is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? The correct answer is whenever an infiltration BMP is proposed. You should assess the hydraulic impact on the groundwater table anytime an infiltration BMP is proposed. This would include any potential drainage issues and potential damage to nearby structures. Number 17, how many soil profile pits and/or soil borings must be performed for 5 small-scale bioretention basins in one mapping unit that are each 450 square feet and scattered around a development? Correct answer for this one is C, 1 soil profile pit for the soil mapping unit and 1 soil boring for each small-scale bioretention basin. So we know from Lisa's soil testing presentation that if an infiltration BMP has an infiltration area that is less than or equal to 500 square feet, you would have to do a minimum of 1 soil profile pit per soil map unit. You would also have to do 1 soil boring per BMP as well. If the BMPs are going to be located in different soil map units, each unit must have 1 soil profile pit. But if you read the question here, the 5 basins are going to be in 1 map unit. So in total, 1 soil profile pit for the 1 map unit in this example, and 1 soil boring per small-scale bioretention basin. Question 18, true or false? In a small-scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the surface of the sand layer. This statement is false. As stated in the BMP manual, for any designed infiltrating BMP, the separation from the seasonal high water table needs to be measured from the bottom of the sand layer, which is the lowest excavated elevation in the BMP. We mentioned the seasonal high water table separation requirement when we talked about why soil testing is important. Question 19. Where on the soil horizon should soil permeability tests be performed when no soil replacement is proposed? And the correct answer is A. Soil permeability tests must be performed on the most hydraulically restrictive soil layer below the BMP and above the seasonal high water table or bedrock, to the greater of 8 feet below the lowest point of the basin, or 2 times the maximum potential water depth, as the permeability of this layer will be the limiting factor in infiltration rates. All right, so that's the end of the quiz review, and that's also the end of Module 2. The next section is going to be on Tuesday, September 16th. I would like to thank everyone for their attendance and participation, and I hope to see you all for Module 3.